Begin by gathering as much information as possible about the existing electrical system. Firstly, ask the utility for detailed information, including transformer ratios and phasing. Secondly, inquire whether the maintenance staff possesses any documentation or records pertaining to the electrical system. Thirdly, look for tags or markings on the transformers or existing motors that indicate voltage and phase configuration. Determine the voltage rating of the existing motors. If they are rated for 208 volts 3-phase, they may not be compatible with the new 120 volts phase. Consult with motor manufacturers or an electrical expert to verify compatibility. It is theoretically possible, but rare, that 2-phase power is derived from a 3-phase source. This involves using a motor starter or transformer to convert 3-phase power to 2-phase. Another possibility is an open delta system, where only 2 phases of a 3-phase system are used. It is also possible that the building is only receiving single-phase power from the 2 transformers. Enlist the help of a qualified electrician to open up equipment and inspect the existing wiring, transformers, and motors. This will help determine the actual voltage and phase configuration being used. If necessary, consider installing a voltage converter to transform the 120 volts phase to the required 208 volts phase. If the existing motors are not compatible with the new voltage, they may need to be replaced. Ensure that the new service upgrade is designed to accommodate the existing load and any potential future expansion needs. Keep the utility informed of your findings and plans, as they may need to make adjustments to their equipment. Inspect the existing generator to ensure it is compatible with the upgraded service. Consider installing a power factor correction system to improve the efficiency of the electrical system. Consult with a local electrical engineer or contractor for guidance and support throughout the process. The primary objective is to understand the existing electrical setup, because it is essential to determine whether the existing system is genuinely a 2-phase system, a 3-phase open delta system, or a single-phase system derived from the 2 transformers. Verify the voltage and phase configuration at the service entrance and at the distribution panels. A 2-phase system is distinct from a 3-phase system. A 2-phase system has 2 alternating current voltages that are 90 electrical degrees apart. A 3-phase system has 3 alternating current voltages that are 120 electrical degrees apart. The original description mentions a generator, which is a critical component. Verify that the generator's output voltage and phase configuration match the building's electrical system requirements and is compatible with the new upgrade. Examine the generator's wiring and connections and make sure they are in good condition. Document the nameplate data on the generator, including voltage, phase, power rating in kilowatts or kilovolt amps, and frequency. Check the generator's automatic transfer switch, or ATS, which is a device that automatically switches the building's power source between the utility power and the generator. Inspect the ATS to ensure that it is functioning correctly and that it is compatible with the new electrical service. Confirm that the ATS is rated for the appropriate voltage and current. Examine the building's grounding system, which is essential for safety and proper equipment operation. Verify that the grounding system is properly installed and that it meets the requirements of the National Electrical Code, or NEC. Check the ground resistance and make sure it is within acceptable limits. Consider using a ground resistance tester to measure the ground resistance. Ensure all grounding conductors are properly sized and connected. Determine the actual load in the existing electrical system. Conduct a load study to determine the current demand of the building's electrical system. Use a power quality analyzer to measure voltage, current, power factor, and harmonics. Use the data from the load study to ensure that the new electrical service is adequately sized. Consider future load growth when sizing the new service. Harmonic distortion can cause equipment to overheat and malfunction. Consider using harmonic filters to reduce harmonic distortion. Verify the short-circuit current rating of the existing electrical equipment. The short-circuit current rating is the maximum amount of fault current that a piece of electrical equipment can withstand without failing. Use a short-circuit analysis to determine the available fault currents at the service entrance. Ensure that the existing electrical equipment has a short circuit current rating that is greater than the available fault current. If necessary, replace equipment with higher short circuit current ratings. If the existing motors are not compatible with the new voltage, consider using variable frequency drives, or VFDs, to control the motors. VFD can adjust the voltage and frequency supplied to the motors, which can allow them to operate at different speeds and voltages. VFD can also improve energy efficiency and reduce motor wear and tear. Consider installing surge protection devices, or SPDs, to protect the building's electrical equipment from voltage surges. SPD can divert voltage surges to ground, preventing them from damaging sensitive electronic equipment. Install SPD at the service entrance and at distribution panels. Consider using a power management system to monitor and control the building's electrical system. A power management system can provide real-time data on energy consumption, power quality, and equipment status. Power management systems can also be used to optimize energy usage and reduce operating costs. Verify the existing wiring insulation. Insulation can degrade over time, which can lead to electrical shorts and fires. Inspect the wiring insulation for signs of damage such as cracks, brittleness, and discoloration. Use a megameter to measure the insulation resistance. Replace any wiring with damaged insulation. Verify the existing conduit system. The conduit system protects the wiring from physical damage and provides a path for the wiring to be installed. Inspect the conduit system for signs of damage, such as corrosion, cracks, and dents. Repair or replace any damaged conduit. Consider using flexible conduit in areas where vibration or movement is expected. Verify the existing overcurrent protection devices, such as circuit breakers and fuses. Overcurrent protection devices protect the wiring and equipment from overloads and short circuits. Ensure that the overcurrent protection devices are properly sized and that they are in good working condition. Test the overcurrent protection devices to verify that they trip at the correct current level. Replace any defective overcurrent protection devices. Consider using arc fault circuit interrupters, or FSIs, to protect against arc faults. Arc faults are a type of electrical fault that can cause fires. FSIs can detect arc faults and trip the circuit, preventing a fire. Install FSIs in branch circuits that serve bedrooms and other areas where arc faults are more likely to occur. Verify the existing lighting system. Lighting can account for a significant portion of a building's energy consumption. Consider upgrading to energy-efficient lighting, such as LED lighting. LED lighting uses significantly less energy than traditional lighting and has a longer lifespan. Consider using lighting controls, such as occupancy sensors and dimmers, to further reduce energy consumption. Occupancy sensors turn off the light when a room is unoccupied, and dimmers allow you to adjust the light level to suit your needs. When upgrading the electrical service, follow all applicable codes and standards, such as the National Electrical Code, or NEC, and local building codes. Obtain all necessary permits before starting work. Use qualified electricians and contractors who are familiar with the NEC and local building codes. Ensure that all work is inspected by a qualified electrical inspector. Document all work performed, including wiring diagrams, equipment specifications, and test results. Keep the documentation in a safe place for future reference. After the upgrade is complete, conduct a thorough testing and commissioning process to ensure that the electrical system is functioning correctly. Test all equipment and systems to verify that they are operating within their specifications. Train the building's maintenance staff on the operation and maintenance of the new electrical system. Provide them with the necessary documentation and resources. Schedule regular maintenance inspections to ensure that the electrical system continues to operate safely and efficiently. By following these recommendations, you can successfully upgrade the building's electrical service and ensure that it meets the current and future needs of the building. The NEC provides tables for allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius to 90 degrees Celsius. Termination provisions for circuit breakers, switches, and so on are listed. Equipment is designed differently. Unless the equipment is marked otherwise, conductor ampacities used in determining equipment domination provisions are based on Table 310.15b16, which is typically 60 degrees Celsius for equipment rated 100 amps or less, or marked for 14 to 1 AWG conductors, and 75 degrees Celsius for equipment rated over 100 amps, or marked for conductors larger than 1 AWG. The information provided by the utility company is paramount because their infrastructure feeds the building. They would possess records of the transformer configurations, voltage levels, and overall system design. This information would be crucial in understanding the existing electrical service and in designing the upgrade. Ask the utility company to provide detailed diagrams of the transformer connections. Ask for the kVA ratings of each transformer. Ask for the primary and secondary voltages of the transformers. Ask for the impedance of the transformers. Ask for any available documentation on the existing electrical service. Existing documentation on the building's electrical system can provide valuable information about the original design and any subsequent modifications. Review any available blueprints or wiring diagrams. Review any available inspection reports or maintenance records. Review any available documentation on the existing equipment. If the utility company and documentation do not provide clear answers regarding the power system, an investigation is required. First, confirm whether the system is two-phase, three-phase open delta, or single-phase. The system could be a single-phase center-tap 240/120 volt service, which is the most common single-phase configuration. This would be fed by two transformers connected to different phases of the utility's distribution system. The system could be a three-phase open delta 240 volt service, which is less common than a true three-phase system. Open delta configurations are sometimes used when the load does not require the full capacity of a complete three-phase bank of transformers. Open delta systems are not as robust as a full three-phase system and can have voltage imbalance issues. An open delta configuration would be fed by two transformers connected in an open delta configuration. It's important to positively identify the voltage and phase configuration to ensure that any new equipment is compatible with the existing system. If existing motors are rated for 208 volts three-phase, they would not be directly compatible with a 240 volts single-phase system or a 240 volts open delta system. The new 208/120 volts service is compatible with new and common electrical equipment, but compatibility with equipment currently installed is key. Verify whether the existing motors are rated for 208 volts three-phase or 230 volts three-phase or some other voltage. If the motors are rated for 230 volts three-phase, they may not operate efficiently or reliably on a 208 volt system. It may be necessary to replace the motors with motors that are rated for 208 volts three-phase, or to use buck-boost transformers to increase the voltage to 230 volts. Assess the condition of the existing motors. Have a qualified electrician inspect the motors for signs of wear and tear, such as cracked insulation, loose connections, and corroded windings. Have the electrician test the motors to verify that they are operating within their specifications. If the motors are in poor condition, it may be more cost-effective to replace them than to try to make them compatible with the new voltage. Electrical plans and upgrades should account for potential future loads. Electrical load calculations should be performed to determine the minimum size of the new electrical service. It is generally a good idea to oversize the new service slightly to allow for future load growth. Consult with the utility company to determine the available capacity of the distribution system. Coordinate with the utility company to schedule the service upgrade. Because the existing building's electrical system is so old, there may be some unexpected issues that arise during the upgrade process. Be prepared to deal with these issues as they arise. Keep a detailed record of all work performed, including wiring diagrams, equipment specifications, and test results. This documentation will be useful for future maintenance and repairs. A power factor correction system is a system that improves the power factor of an electrical system. Power factor is a measure of how efficiently electrical power is being used. A power factor of 1.0 indicates that electrical power is being used perfectly efficiently, while a power factor of less than 1.0 indicates that electrical power is being wasted. Power factor correction systems can improve the power factor of an electrical system by reducing the amount of reactive power that is being used. Reactive power is the power that is required to create and maintain magnetic fields in electrical equipment, such as motors and transformers. By reducing the amount of reactive power that is being used, a power factor correction system can reduce the amount of current that is flowing through the electrical system. This can lead to lower energy costs, improved voltage regulation, and reduced equipment heating. There are several different types of power factor correction systems available, including capacitor banks, synchronous condensers, and static VAR compensators, or SVCs. Capacitor banks are the most common type of power factor correction system. They consist of a bank of capacitors that are connected to the electrical system. The capacitors store reactive power, which can then be released back into the system when needed. Synchronous condensers are rotating machines that can generate or absorb reactive power. They are typically used in large industrial facilities. SVC are electronic devices that can control the flow of reactive power in an electrical system. They are typically used in high voltage transmission systems. The best type of power factor correction system for a particular application will depend on the specific requirements of the electrical system. Factors to consider include the size of the electrical system, the amount of reactive power that is being used, and the desired level of power factor correction. Power factor correction can also reduce carbon emissions. By improving the efficiency of electrical systems, power factor correction can reduce the amount of energy that is required to power equipment. This can lead to low carbon emissions from power plants.